I'm Bruce Bugbee, and this is a continuing series of seminars on principles of environmental measurement. In this next mini seminar, we're going to talk about radiation shields. How do you protect a sensor from solar radiation to shade it, to get it to more accurately measure true air temperature? Now this is something, like many things, that we thought we knew how to do 10 years ago, and we start to do more rigorous tests, and then we start to find out the things we don't know. So we're going to talk about the past 8 years of research on radiation shields and how we've modified shields and come up with a new type of shield that uses less power and is more accurate than the traditional things. I'm joined in this effort by Mark Blomquist, the chief scientist at Apogee. He and I have been doing tests on this in many places over a lot of time to get this data. So let's take a look at the types of shields. Now here's a great picture of these shields against the sky, and it summarizes the 5 types of shields I'm going to talk about in here. This is at an angle, so there's a little bit of wide angle distortion here, but let's go through them. Here's the shields that everybody is familiar with. We call these multi-plate shields. They're also called passive shields or static shields. There's no moving parts. They rely on the wind to cool it off. The wind's supposed to go through them, and it's supposed to shade the sun. They've been used on hundreds of thousands of weather stations over many decades. Now let's look at how accurate they are compared to improvements. So here's one type. This is one made by MetSpec in England. Here's a second type right here, which is made by R.M. Young. These come in multiple heights. We used ones that are tall, so the very best of this technology, but we compared it to 3 active shields that have a fan in them. And it's pretty simple. If you have a fan blowing over something, it doesn't heat up in the sun the way a static shield does. So as you can imagine, if the sun is bright and the wind is not blowing, these heat up above air temperature, and with the fan, the problem is greatly diminished. So in this series of tests I'm going to show you, we looked at the Met-1 shield, which is a long tube. It's actually the biggest of the 3 shields, and the inlet to the air comes in the bottom, right there, and then the outlet of the air comes out the top, up here. The second shield we looked at is the R.M. Young shield. Again, the air is coming in the bottom, blowing out the top. And the third shield we looked at is an Apogee Fan-aspirated Shield. Same thing, air's coming in the bottom and out the top. So we'll look at the data, and then we'll look at some of the physical principles that result in air temperature. So after years of work and refining that design, the next step is field testing, and we've tested these now in multiple locations. So before I show you the data, let's look at the locations. One of the first test sites is at Campbell Scientific here in Logan, Utah, and here's the multiple replicate shields you can see on this screen. MetSpec shields, small multi-plates, big multi-plates. Here's the Apogee shield right there. Here's an R.M. Young shield there, compared to all these other shields. And look at it, here's the anemometer for wind speed. So this is one of the test sites run over an extended period of time to look at differences in measurement accuracy caused by shields. Now these all have accurate temperature sensors inside them to make this a fair comparison. Next site is Apogee's backyard, which is a more extensive test. You can see all these along a plane. Here's replicate Apogee shields. There's many of them. Here's the Met-1 shield. Here's the R.M. Young shield. There's many replicate shields in this. This is in a line, but we filtered the data for only when it was crosswinds to get more precise data out of this test. All run off a single weather station. It's an example of some of the testing we've done. Third site is Campbell Scientific England. Same thing. Here's the R.M. Young. Here's the Apogee, whole bunch of static shields in this test, all hooked up to a common data logger, run over a long period of time to test for differences among shields. Another site is the Utah State University Campus Environmental Observatory, which is a solar-powered station right in the middle of campus. And here's a static shield, and here's an Apogee shield in comparison in that. Typically, we have the inlets of these at the exact same height. They're not quite that way here because the ground is warm, and the higher you go, the cooler it is. So this test would slightly favor the static shield over this because this is lower and this is higher. But typically in all the other tests, the inlets were at the exact same height. Now let's look at some of the data from these tests. We're going to summarize a lot of data in a few slides. Here's the raw data, these two slides. Here's the summarized data. So let's look at the summarized data first without all these data points in it. This is the temperature rise above the active radiation shield. Now, all three of the active shields were very close to each other, so they're very close to zero. And if the wind is blowing, now let's look at two things. Here's a small thermistor, right here, the blue line. Here is a larger humidity probe. How do people measure temperature in these? A humidity probe. So if you have a larger humidity probe, you can have 1 degree C errors in still wind if the sun is out. If the wind is 3 meters a second, a gentle breeze, you still have, you can see about 0.3 degrees C error, all the way up to a rigorous breeze. Flags would be standing straight out at wind speeds like this. It still didn't, the humidity probe still didn't get quite to zero. So the small thermistor was better, and let's see here if we can erase some of this. This is our new board. It's just like a blackboard, only no chalk. So now we go to this. Get back to green. Now let's look at this small thermistor. Much better because it's small. This is a tiny yellow bead thermistor made by Apogee Instruments. Very tiny. Look at this. At 3 meters a second, now the error gets less than 1/10 of a degree C, but it's a pretty big error below that. And finally, this gets very close to zero out here at high wind speeds. This is just the raw data, because these are short time intervals, there's little puffs of wind, but the key is that summary there. Small thermistors are more accurate than larger humidity sensors, and we'll get back to that, but that's a key distinction because people often just use the humidity sensor to measure these, and they use it in a static shield. So what's the next data look like? This is differences in the static shields. This is the R.M. Young shield, which is a very widely used shield on weather stations. That had the greatest temperature increases in our tests, greater increases compared to the Met-Spec shields. Met-Spec has two models. Here's the 1, shown in green. Here's the 2, shown in blue. The MK1 was slightly better, but still they didn't get down to zero until there was a reasonable breeze blowing to cool it off. These three show the raw data, all feeding into this summary. So shields vary a little bit, but even the best shields had errors in temperature. So what happens in the winter? Winter is a killer. There's snow in the ground, there's low angle light reflecting up on these shields, so the radiation intensity is focused on the shield. They're not designed to block low angle radiation. Remember, the shields have a design that looks like this. Yeah, what happens when the sun comes in like that? It heats it up, gets right inside. Here's the data for no snow on the ground. This is over vegetative surface. Once the sun comes out, the errors start to approach 2 degrees C with no wind, and they don't go to 0 until we get a very stiff breeze blowing on these. So the errors are much worse over snow. Let's take a look now at the small differences between these 3 types of aspirated shields. These are the R.M. Young shield and the Apogee shield compared to the MET1 shield. Now in our tests, the MET1 shield read slightly cooler, so we use that as the reference here. There is no official reference for this. At 0, things heat up as the radiation gets bigger. So here's temperature errors in the summer, and they're less than 0.05 degrees C. The Apogee shield was slightly better than the R.M. Young shield for accuracy and in these tests, but now look at the winter. Much worse. But remember, the static shields were more than 1 degree C above air temperature. Now we've reduced that error to less than 0.1 degrees C, even in the winter with the reflected light. And of course, when it's dark, there's no error at all. So these are all close. The Apogee shield in these tests outperformed the R.M. Young shield and was very close to the MET1 shield. So how does this Apogee shield work? One of the design goals of this was to dramatically reduce the power to the shield. And let's take a side view look at this thing. Because if you're going to run these from a solar powered system, you either need an enormous solar panel or a more efficient design. This is the Apogee design right here in side view, filled with foam, sensor port adapter right here, going to the sensor. Now this is what's called a coanda inlet. And it looks like a jet engine inlet, so that when the wind is blowing sideways, it can more easily change direction and go up here in the fan and blow out the top of the shield. If this was a square edge, like it was in all of our early tests, anytime there was a crosswind, we had problems. So we had to go to this specialized coanda inlet, coupled with a small sensor in just the right place. Notice the taper here. That's a rocket nozzle contour to get the wind going faster and faster over this shield right here. These are all critical to the design and critical to the use of a small fan. Here's the whole thing sealed up here. It's G-Loy plastic, Venturi contour inlet. Let me, now that we're here, let me show you some of the component parts. Here's the fan. This is an IP55 rated fan that's custom built for Apogee. IP55 is a measure of the resistance to water and dust. You can spray this fan with water and it doesn't hurt it. We have yet to have, in spite of now having several hundred of these in the field in very rugged environments, we have yet to ever have a fan fail. And some of them have been out for 4 years now. It's rated for at least 50,000 hours. So this is an exceptionally rugged, small, low-power fan. This coanda radius, we got it right here. Here it is. There's the coanda radius, so the air can come right up in here and the fan sits right in here and blow out. Now, this whole thing is covered by a hat so that we can shield it from the sun and water, and it's a simple yet elegant design. So let's take a look at some performance data. Here's the coanda. You could see the difference in fan size. R.M. Young 400 milliamp, Apogee 80 milliamp. This is a 5-fold reduction in power for the fan. So much smaller battery, much smaller solar panel, it gets better. At night, you don't need to run the fan full blast. So Apogee has put in a variable speed fan, which I'm going to talk about in the next slide. But this is the difference in the coanda radius. When the wind is blowing sideways, the RMM got worse, and because of that radius, the Apogee gets better, slightly better with high wind, in spite of a 5-fold reduction in speed. Now let's look at the variable speed fan. Here it is, running full blast, 80 milliamps with the ratio of 1. At night or on cloudy days, with a PWM command, we can slow the fan down all the way to 25 milliamps, and now the wind speed is less, but the power consumption is much less. So it's already a small fan, and we can further optimize it by slowing it down at night and on cloudy days, or on days when the wind is already high. Don't need a fan. Here's the IP55 rating. Tachometer output. So this is a separate wire to the data logger telling the RPMs of this fan. If anything gets in there and the fan's not working right, we'll slow it. It'll show up and raise a red flag. This is how we save power. Pulse width modulation from the data acquisition system. So there's a top view of the fan right there. How do you get the sensors in this? Other shields, they're big, you put them in from the top, you clamp them in. After lots of testing, we found the best way is put them in the side. Here's the picture, here's the shield, the sensors go right in the side like this. It's simple, it's elegant. You can take out sensors and change them. You can put in multiple sensors. Here's a bunch of pictures of what we call sensor port adapters. So if you need one thermistor, this is the sensor of choice. If you want to have replicates, there's 2 replicates, 3 replicates, 4 replicate thermistors for super precision work. It's easy to do. These are cheap and easy to make. Now what if you want a humidity probe with it, like everybody does? Here we go. You buy the model with a humidity probe adapter, and that looks like this. Here's a picture of that adapter. It clips right in here, quarter turn, snaps into place, O-rings to hold the humidity probe in place. So these come in all shapes and sizes to hold a wide range of sensors. Here is a picture of one in action. It would sit like this in the shield. The air is coming up like this. We accurately measure the temperature there, and then the humidity here. This is if I say the HMP 110, shown with how this would go right into the adapter. So this is easy to do for a wide range of sensors, and they're easy to take out and clean. That's another thing. These eventually get dirty. In other shields, you take the whole shield apart. Here, you just pop the sensors out, wipe them clean, put them right back in. That was another design feature that we put into this. There's a picture of that in the field. So these are the air temperature options for this. The Apogee ST110 is that yellow bead thermistor. Now, many places call for more precise data with the platinum resistance thermometer, and here is an example of that with a 4-wire PRT in that sensor port adapter for places that require PRT accuracy measurements. This is another probe that works fine with it, the Campbell Scientific 109. A wide range of temperature sensors work fine. Visela, Campbell Scientific, Rotronics, EE Electronics. It works fine with a wide range of sensors, just with the right sensor port adapter. Of course, many people buy more than one sensor port adapter for future expansion. Here's a couple case studies in the field where this has been used. This is what's called the I-Utah project. And they use a lowercase I to be high-tech. There's many of these stations in the mountains of Utah monitoring snowmelt, where Accuracy of air temperature is everything. How fast does the snow melt in the spring? How fast does the water run down in the valley? If we're off 1/10 of a degree C, the models are wrong. We have to have accuracy. There's the Apogee Shield. This, by the way, is an Apogee heated pyranometer, which they've selected for use on this for extreme winter conditions. This is just an example. Up in the mountains, the snow gets deep, so this stuff has to be high up. One more example is a greenhouse environment. This one happens to be Roberto Lopez's greenhouse at Purdue University. He ordered multiple Apogee sensors for precision air temperature measurement over his experimental plots. So here they are with the precision thermistor coming out and the shields, multiple replicate shields hanging in a greenhouse. So, in summary, the Apogee Shield has been optimized for accuracy and low power and low cost. Those three things we think make it a very favorable choice for weather stations when precision air temperature measurements are important. This can replace the old static shields for precision air temperature measurement. And I'll stop there. That's the final slide in the shield measurement series. We hope to see you again in another measurement seminar. Thank you.